All right. So now we will do several things. First, we'll connect the idea of heat capacity to modes, and then we will go a little bit deeper into the idea of heat capacity and compare experiments that are done at constant volume versus constant pressure. Okay, so the microscopic versus the macroscopic description of heat capacity. So kind of going back to E-thermal and what it's proportional to from the way we define it at the start of the quarter. So first, let's start with our conservation of energy equation. We saw, we're talking about only E-thermal and E-bond, that the changes in E-thermal plus E-bond have to equal to heat plus work. Then we also defined heat capacity, and by definition, the heat capacity is Q over delta T, so it's the amount of heat added to the system to give you that temperature difference. Now, when we set work equals to 0, and we will later relate that, so for now, I'm just telling you that's true for when the process is at constant volume. We'll see more of that coming up in the next few recordings, but for now, just kind of take it as fact. So when work is 0 and when there's no change in bond energy, no phase change, so we're only focusing on temperature change, then this simplifies as to delta E thermal, will just equal to Q, and then we can rewrite Q in terms of heat capacity times delta T. So in the beginning of the course, we kind of just went directly to this. Delta E thermal is C delta T, because we assume these things of no phase change and no work being done in that particular process. So can we relate now this, or specific heat capacity, and then specific heat to the modes that we've been talking about? Okay. So macroscopic is something that's on the order, let's say, of 1 mole, and we're focusing here on constant volume. This is what's allowing us to set work to 0. We saw that using, again, our original definition of thermal energy, we can put in 1 mole, and then we define the specific heat. Now we're adding a couple of more subscripts. We're being not very rigorous about this in the beginning of the quarter, but now we will be, because we're going a little bit more into depth. So constant volume, that's what the V stands for. And then mole, it just means it has the molar units rather than the specific heat which we define in terms of mass or kilograms. So we can rewrite it this way, times delta T. Now, the microscopic definition of thermal energy, which is what we have been working with more recently, for 1 mole would be, first remember we count the total number of modes, so it would be the modes per particle times that 1 mole. We're just comparing the molar definition here, times 1/2 kb delta T. So you could see now it's the same type of energy, this delta E thermal. We could see now that we can just take these prefactors and set them equal to each other. So if we equate the above equation and then we solve for specific heat, we find that it's 1/2 times this modes per particle times R. I don't know if I write it out. Yes, I do. So this R is just a new constant. It's known as the gas constant, and that's just because you see here a factor of Na, which is Avogadro's number, times Kb. So instead of always having to multiply these two numbers together, which are both kind of bulky numbers, it's easier to work directly with this gas constant, which ends up being 8.314 joules per mole per Kelvin. So what do we find here? We find that our original macroscopic definition of thermal energy, which connected thermal energy to temperature in terms of specific heat. So again, to figure out the specific heat, we didn't need to know anything about what are substances made out of. We didn't need to know anything about that it's made out of atoms or molecules. All we needed to do is go to some lab, heat it up, kind of measure how much energy we put into our system, measure the temperature change, collect some data, and that would give us this specific heat. But now we have this equation that connects this to the kind of in a very simple way to the atomic picture of what's going on in terms of how this energy is being distributed um, uh, uh, in these atoms or molecules, depending on how it can store this energy. So this modes, the number of modes per particle. So it's kind of an interesting result, and you could see probably already kind of sense that this must be pretty simplified, because what is this telling us? It's telling us that all types of monatomic gases should have the same specific heat, or all solids or all liquids. And we, from working back in the beginning of the quarter, we saw that there were differences, but it turns out that this model is actually not so bad. So let's, in a couple of slides, we'll look at some data. But before then, I just wanted to, now that we have defined heat capacity or specific heat, to be exact in terms of modes, to look a little bit deeper into this freezing out of modes. So what you see here, and you'll study this plot in quite some detail in DL, but I just wanted to summarize it a little bit here. So what you see here on the y-axis is, although it's kind of written here as a capital letter, this is really meant to be specific heat, the smaller specific heat at constant volume over R. So really what's on the y-axis, if we go back to the previous slide, CV over R is just 1/2 times the number of modes per particle. Okay, as a function of temperature. So this graph displays this idea of freezing out of modes, or these modes per particle depending on temperature. So you could see for gases, it's always going to be 3 modes per particle, because you can never freeze out the translational kinetic energy modes. They're always there as long as you're above 0 temperature. So only exactly at absolute 0 temperature, when all motion is frozen, although quantum mechanically it's not quite true, but classically when all motion ceases, so at 0 temperature, there wouldn't be those modes. But anything above 0, this ranges from about 300 Kelvin, around room temperature around here, to very high temperatures of 2000 Kelvin, you will always have these 3 modes. So this is, remember, modes divided by 2. So to get actual number of modes per particle on this y-axis, you have to multiply by 2. So 1/2 times 2 is 3. All monatomic gases will have these 3 modes. Now let's look at diatomic gases. So that's 2 atoms. So H2 is an example of one, and 2 Cl2. What do we see? That at low temperatures here of about 300 Kelvin, the number of modes is 5, because remember, we have to always multiply by 2. So 2.5 times 2 gives us 5. But then as we increase temperature, it seems to reach this value of 7/2. 7/2, which is times 2, 7. So we start at 5 modes. And what is that 5 modes? That's exactly when those vibrational modes are frozen, because then we have the 3 kinetic energy modes, translational, and 2 rotational, gives us 5. And 7 is the maximum number when now we have these vibrational modes present. So 1 kinetic, 1 potential vibrational mode. So that's a possible range from 5 to 7. You might ask, actually, why is it kind of going smoothly? Like, what's the meaning that at 500, let's say, degrees Kelvin, we have something like 2.8 times 2, so 5.2 modes. How is it possible to have a non-integer number of modes? Well, it's not. But what this is data collected, let's say, for a mole of particles. So this is an average number of active modes per particle. So maybe, when we're over here, on average, Majority of them still only have 5 modes active, but maybe some of them have already activated the vibrational modes, but majority still have active, or have them frozen. Where somewhere in between here, it's about half and half. So half of the particles on average have the vibrational modes activated and half don't. So that because it's an average, you get these non-integer values, basically. Now, if you look at some more complicated molecules, like this is, CH4, NH3, or CO2, you could see now that, the more atoms in the molecule, the more modes it's possible to have. So this kind of graph keeps on going. But another thing that's true, as you keep on increasing temperature, there's going to be a limit after which our molecule can not have more active modes. So it's not like these number of modes go to infinite number. You've done the calculation. It's 6n for a nonlinear molecule. It ended up being 6n minus 6. So that will tell you the maximum number of active modes you can have. But these all these molecules here start around 7. And we don't exactly necessarily know which ones are active or which vibrations become active first versus later. But typically what is known is that the rotational modes are active at lower temperatures, like room temperatures. They also become frozen at temperatures, much lower than room temperature. But around here, normally what's active is the rotational modes. And then as you increase temperature, some of these vibrational modes become active. But again, you'll think more about this in discussion lab. All right, so moving on to what we have just learned, let's go back here. That's kind of our big result here, connecting specific heat to modes per particle. So let's look at some data. See how good is this model. So this is specific heats for a bunch of solids. So you have here quite a big list of different solids. If we use our model, which is 1/2 times the modes per particle, we're talking about solids, so this has to be 6 times this constant, you can plug this in, you get close to 25 joules per mole per Kelvin. So if you look at this plot, and with the 6 modes, this is around where 25 is. So you could see that on average, it's not bad model. So a lot of these solids do have the same heat capacity of close to 25, but there's some weird ones, like diamond seems to be quite different. Graphite, water is always an odd one, silica here. So there's clearly, this model is not sufficient to describe all types of phenomena, and it's beyond the scope of the course to kind of go into details of why these particular substances are so different, but you could see that for majority of solids, at least, this model works pretty well. Now let's look at some gases. So here we have a plot where we have a mixture of monatomic gases, so like neon, helium, argon, mercury, and then I believe that like air, nitrogen, I think this is referring to diatomic, and then water is even more. It's triatomic because it's H2O. So let's see how well our model describes this. So if we focus just on the monatomic gases, use this equation, instead of 6, that's a 3 now. So we should get 12.5. So if we draw 12.5 here, it doesn't seem to agree at all with anything. Like helium should be monatomic, argon, neon, but it's bigger. Here the data shows. The same with the diatomic gases. If we were to solve for that and plug in 5 here, we should get about 20, which is this line, but these are the diatomic ones here, starting with the hydrogen. So I think it says here, it says hydrogen, but it really means H2. And then air is normally a combination of a bunch of diatomic gases. So, but this line is basically falling short. So something is going on. Our model worked pretty well for solids, but it's not seeming to work too well for these gases. So let's take a look more carefully what's going on here. Okay, so there's more to the story. There's different experiments that we can do that are slightly different. So remember, um, I think we started this, yes. So at the beginning of this recording, I kind of stressed the fact that in order to make that connection between heat and specific heat, so Q and specific heat, we had to assume that the experiment is happening at constant volume. So there's some important implications of that. So what does constant volume mean? So that's what the V is, CV measurement. It means that you have a container which is closed. If it's a closed container, your gas, and we're talking about gases here only, your gas is kept in a constant volume. What that tells us that all the heat that you add to this container, assuming it's not being lost to the environment, will go into the gas as energy. So you Q in that definition of specific heat is the heat added. Now, if your experiment is done at constant pressure, so what we're trying to do now is keep the pressure constant. The only way to do that is to allow, and in the next couple of weeks, we'll start talking about thermodynamics and we'll introduce ideal gas law. So you will see this connection between pressure, volume, and temperature. But basically, to keep the pressure constant, you have to allow the volume to change. So it's no longer a constant volume experiment. And you allow the volume to change by kind of allowing this container to be open. Or you can think about it that there's some kind of very light lid on the container that's allowed to move up and down as heat is being added. So, but in order for this container to expand, what has to happen? Well, there has to be a force that allows it to expand. And if there's a force, some of that energy you put in goes into that work being done to expand that container. So here, when we're basically talking about constant pressure experiment, we can no longer neglect work. And I will define work more formally in the next couple of lectures and recordings, but for now, all you can think about is there has to be some of the work being done. So some of that heat is going into heating up the substance, but some of that heat is going into doing that work, which pushes this, like, let's say, air here out of the way, allowing this gas to expand. Okay, so based on what I just said, I just want you to think about quickly, what do you think should be bigger, or should they be the same? Heat capacity or specific heat, here, little c, specific heat at constant volume or at constant pressure. So these two experiments, which one should be bigger? So pause the video, think about it, and let's see. So I claim that CP should be bigger. So why is that? So what did I say was special or different about this experiment done at constant pressure? What was different about it is that the heat that you added, some of it went into changing the temperature or into the substance, but some of that heat left the system and form of work by by exerting a force on the air and expanding the volume. Now, what's the definition of heat capacity and specific heat? It's Q over T. So in order to have that same increase of temperature, you have to add more heat in a constant pressure experiment. Why again? Because not all of that heat is going into the thermal energy. Some of it is leaving the system. So you have to add more. So the Q has to be bigger to have the same T. Actually, it should be a delta T here, which tells us that the specific heat at constant pressure is indeed bigger. Okay, so maybe now we can try to fix that previous result, because typically when experiments are done for gases, or that data I happen to show you is done at constant pressure. So let's kind of try to use this ideas to try to change our model to be suitable for constant pressure experiments. Okay, so how do we do that? So let's go back to this equation of our most general equation for conservation of energy. Bond energy is still zero. We're still only talking about thermal energy, but now we can no longer neglect work. So if we rewrite now our C, our heat capacity, but now we say that that heat capacity is due to an experiment done at constant pressure. It's still Q over T, but now Q is no longer just equal to E thermal, but it's equal E thermal to minus work. So then if we rewrite this, we see that, okay, delta E thermal over delta T, that's exactly by definition heat capacity at constant volume, but now we are subtracting this term, which is work over delta T. And in order to kind of take a step farther in this derivation, we need to know a little bit more about what work is and how pressure, volume, and temperature is connected. So that's coming up next in the next couple of recordings. So I won't get into this derivation quite yet here, and you will do this also in DL. So I'll kind of leave it at that, and I will just give you the final result, that the relationship between CP and CV is this. You see that here it seems like we're subtracting something from CV, so CP should be smaller than CV, but it turns out, and again, I won't get into this quite yet, that work is negative in this case. So then it ends up being a plus. So when you work all of this out, what you get is that CP is CV plus R. So in fact, specific heat at constant pressure is bigger than specific heat at constant volume, and exactly by this factor of R. So if we go back to our calculation, what we were comparing before is the equation for CV. And that's why we were coming short. Remember, we got about like 12 for monatomic gas instead of 20, and we got around 20 instead of, what looks like closer to 28 for diatomic gases. But here you see that this data shows CP at constant pressure. So we weren't doing the right thing. And if we actually, and you'll do this again in DL, recalculate this by adding a factor of R to what we got in the previous couple of slides, we find that now indeed things agree pretty well. That for monatomic gases, we land around there, and for diatomic gases, we land around there, which kind of agrees pretty well. So we didn't make some huge mistake in our model, we just had to modify it. So that's kind of how often science works. You make some model, you find some data, it doesn't fit, and then you try to figure out why that is. All right, so everything worked out at the end. And just to kind of tell you a little bit about what's coming up. So the next big topic in 7A that's coming up is thermodynamics. Although you'll see we'll use a lot of the ideas that we've developed so far in 7A to introduce it and to kind of go into a little bit more depth. So, for example, what is exactly thermodynamics? It's the study of different processes and how energy flows. It's basically another study of conservation of energy, but specific to these thermal systems. So for example, we just saw that two different processes done at constant volume where change in the thermal was heat added, where at constant pressure, different process, we added some amount of heat, but now it's no longer equal to change in the thermal because now there's work involved. So we will look at a lot of these different types of processes and introduce some new processes and kind of develop this general model of thermodynamics in the next couple of lectures. All right, I think that's it for today. So process matters, different processes gave us different results, and that's kind of what thermodynamics will be all about. See you next time. Thank you.